Hello candidates, welcome to yet another segment of magnetism. Don't forget to stay safe, stay indoors. Then don't also forget to subscribe to the channel. It's called Study101, and then you are free to like the videos. Right now we are going to look at the properties of magnets. This segment is going to be in 3 phases. The first phase, we are going to run through these properties. We are going to run through the properties. Then phase 2, we shall perform some practicals. And then phase 3, we shall get to that part where we need to draw. We need to see, in case they tell us to draw any of those illustrations, how do we do it? In case they tell us to illustrate, how do we illustrate? So let's begin with reading through the properties. Property number 1, unlike poles of magnets attract while like poles repel. That is property number 1, and still it is the principle or law of magnets. It is the principle or law of magnets. And I usually want to take it as property number 1. The principle or law of magnets states that unlike poles of magnets attract each other, while like poles repel. So it will also be our first property. We shall perform a practical on that. We shall perform an experiment. Then 2, a freely suspended magnet rests in the north-south direction. A freely suspended magnet rests in the north-south direction. Property number 3, magnetism can pass through non-magnetic materials. We shall see how that experiment goes. Property number 4, magnetism is concentrated at the poles. Magnetism is stronger at the poles. We shall see that experiment too. Then magnetic lines of force of a magnet run from the north pole to the south pole. The magnetic lines of force of a magnet run from the north pole to the south pole. Every magnet has its magnetic lines of force running from the north pole to the south pole, except only one magnet, which is the Earth. So the magnetic lines of force of the Earth run from the south pole to the north pole. Yet all the other magnets, the magnetic lines of force run from the north pole to the south pole. Property number 6, a magnet has a north pole and south pole. Then magnets weaken with age. Age means we need time, that means we shall not do that practical. Broken pieces of a magnet retain their north and south poles. Broken pieces of magnets retain their north and south poles. We are not going to perform that because we don't need to break the few magnets that we have for now. So we are going to begin with experiment number 2. Experiment number 2. We have got a magnet that is freely suspended, and I freely suspended it some minutes ago, like 5 minutes ago, and right now it has rested and it is pointing in the north-south direction. That's my magnet. It's freely suspended. It is resting in the north-south direction. That's a bar magnet which is freely suspended. It is resting in the north-south direction, and that is the property which enables that enables the magnets to show direction. And in our earlier presentation, we also discovered that there's a magnet called a compass needle. So the compass needle is freely suspended on a liquid, on a fluid, in that after as it settles, it is able to show direction. It is able to rest in the north-south direction. And according to this place, we know the sun rises from that side and it sets this side. So this bar magnet is very accurate. Then we are moving to experiment number 2. Unlike poles of magnets attract while like poles repel. I need to show you what we mean by repelling. So this pole and this pole are like poles, so we are going to see what we mean by repulsion. So the magnet I'm holding is repelling this other one. It is repelling, and the magnet, this cylindrical magnet is trying to spin so that it can present the like pole, the unlike pole, so that there is attraction. So that is repulsion. But if we bring like poles together, then there is attraction. Like poles repel, while unlike poles attract. That is experiment number 2. Moving to experiment number 3, magnetism can pass through non-magnetic materials. We have our magnet here. We have our magnet here, and this is a magnetic material. We need to see whether it can get attracted. I hope you're seeing that. It's getting attracted. So magnetism can pass through non-magnetic materials. I can still perform another experiment using the same magnet. I have got iron filings here. Iron filings are magnetic. The paper is non-magnetic, and this is our cylindrical magnet. So I hope you can see that. I hope you can see that. As I move the magnet at the bottom of the paper, we can see magnetism passing through non-magnetic material. Then magnetism is concentrated at the poles. Magnetism is concentrated at the poles. I'm still going to use our iron filings here. Magnetism is concentrated at the poles. I'm using our bar magnet. We need to see how the iron filings concentrate at the poles. When you look at this experiment, you will find the middle of the magnet. The middle of the magnet, the magnetism is concentrated at the edges. These are the poles of the magnet, and the middle there, you find the less of the iron filings. So magnetism is concentrated at the poles. And then magnetic lines of force of a magnet run from the North Pole to the South Pole. I'm not going to perform a practical on that one because our magnets are not labeled. Our magnets, the poles are not labeled. But magnetic lines of every magnet, each and every magnet, the magnetic lines of force run from the North Pole to the South Pole, save for one magnet, which I called the Earth. The magnetic lines of force of the Earth run from the South Pole to the North Pole. That number can come. I can draw for you the Earth and draw the lines of force without arrows, and I tell you, using arrows, show the direction of the magnetic field. So you should be in position to answer that. Magnets weaken with age, we need time to perform that, which we don't have. Broken pieces of magnets retain their north and south poles. Yeah. So we move to the phase 3 of the show. In this phase, we need to see the illustrations. We need to see the diagrams. The first one is unlike poles. Unlike poles the first one is like poles. Like poles, we are basing on the principle to get property 1. Like poles of a magnet, north north, repulsion, south south, repulsion, and X is called the neutral zone or neutral point. Neutral point is that point where that has zero magnetic field. There's no magnetic field in this area, so there's no attraction or repulsion. Then attraction, with attraction we said it occurs with unlike poles, north south, north south. And don't forget that magnetic lines of force of a magnet run from north pole to the south pole. So this is how we draw attraction. With attraction, we have to draw those lines and show the arrows showing the magnetic field running from north pole to south pole. Then this other side, north is here and south is here. So we do not have a specific rule that always north has to come first. Sometimes south has to come first, then so north-south attraction. So this is attraction, and then this is repulsion. That was property number 1. That is how you draw it in case they ask you to draw. The arrows are very important because we said magnetic lines of force of a magnet run from north pole to south pole. Those arrows are very important. It is very important for you to place the arrows the right way. Now that we have south-south, we have the arrows moving from north pole coming to the south pole. Property number 2, a freely suspended magnet rests in a north-south direction. We have two diagrams. For those people who think are very good at pictures, they can draw this one, which looks 3D, which looks 3-dimensional. Then if you think you're not very good at diagrams, at least give us the basic. Label the string, and then this is a magnet. Label the poles. Using ink, you label the poles. Diagrams are drawn in pencil. Diagrams are always drawn in pencil. So far those are 2 properties. Moving to property number 3 in diagrams. Property number 3 in diagrams. Magnetism can pass through non-magnetic materials. We have done this practically. This is the magnet. This can be wood. You can call it a paper. You can call it plastic. And then you put a magnetic material down. And by now we know you can list examples of magnetic materials if you've been watching the previous clips. Or this other one here. This is the glass, then the magnet is inside. We can even put water or not put water. And then out of the glass, remember glass is non-magnetic, so the pin can be attracted through the glass. The property is magnetism can pass through non-magnetic materials. Then property number 4, magnetism is concentrated at the poles. Magnetism is concentrated at the poles. Magnetism is stronger at the poles. So this is what we do, like we saw. It's not easy to deal with iron filings, but if you got iron filings and you sprinkle them onto the magnet, though they are not easy to remove, that is what we shall see. They will concentrate at the poles. So this is a cylindrical magnet with, so these are iron filings. Maybe these are nails. This is a bar magnet with the nails concentrated at the poles. Then maybe this is a horseshoe magnet with the, maybe these are thumb tacks. So this shows, that is how you're supposed to draw it. You don't draw all of these. Choose one magnet, draw magnetic materials at the poles. And property number 5, magnetic lines of force of a magnet run from the North Pole to the South Pole. I wanted to fill in some of these arrows when you're watching. So North Pole, the magnets, this is very basic, very basic. This is the very basic diagram. At least you should be able to do this. Everyone should be able to draw this one. They are running from the North Pole to the South Pole. It does not matter whether it's North Pole first or South Pole or South first or North first. What matters is the direction of the arrows. So other students normally add a few number of lines of force, a few of them. These ones are coming in. They are coming in from a north somewhere. So they are coming in, and these ones are going out to a south somewhere. If we had very good strong magnets with iron filings, we can really see the magnetic lines of force. So seeing it on another magnet like a horseshoe magnet, the magnetic lines of force, still the rule is the same. Magnetic lines of force of a magnet run from the North Pole to South Pole. This one is very basic. This is a bit complicated, but we shall mind the way you place your arrows. We shall mind the way you place your arrows. So they are coming in from a north. From north, we expect arrows going out of north. And on south, we expect arrows coming in. Just like that. Then, finally, property number 6. Broken pieces of a magnet retain their north and south poles. This is our whole magnet. That was the first, when we had one piece. When you break it into 2 pieces, it has to maintain the north and the south. And remember, one of the properties is a magnet has got a north pole and a south pole. So if we are to say that a broken piece of magnet, if a magnet breaks, we get smaller magnets. That means each one of those smaller magnets must have a north pole and a south pole, as shown here. So if this was the south, it will remain south, then this one will remain north. But then in between, we have a north and a south. If we continue to break these further, this is what we shall have. North, we had a south, south, north, north. Then here we also had south, south, north, north. Then these pieces in between will each regain their north or south pole. So that has been this segment. We have looked at the properties of magnetism. We have gone through them. We have done the practicals. On at least like 4 or 5 properties, we have done the practicals. And we have seen the illustrations. We have seen how to draw them in case you really have, in case you're tasked to draw them. Thank you for watching. Don't forget to subscribe and like the video. Bye.